Brass has a density of 8.25 grams per centimeter cubed and a specific heat capacity of 0.362 joules per gram degree Celsius. A cube of brass, 22 millimeters on each side, is heated to a temperature of 85 degrees. It is then dropped into 20 milliliters of water. The density and specific heat of water are given at 19 degrees Celsius in a coffee cup calorimeter. Assuming no heat is lost, what is the final temperature of the water? Okay, so this is classic calorimetry problem here, where when we combine the brass and the water, what we have to realize is the final temperature of the water and the final temperature of the brass will be the same. The brass temperature will decrease as it releases heat to the water, and as it releases heat to the water, the temperature of the water will increase until they have the same temperature. So what we can say is that the heat gained by the water is equal to the minus Q, or the heat lost by the brass. Okay? And so that means MC delta T for the water is equal to MC delta T for the brass. So the mass of the water, if we have 20 milliliters of water at 1 gram per milliliter, that's 20 grams of water. The specific heat, we're told, is 4.184 joules per gram degree C. Then delta T, so it's final temperature minus initial temperature. We don't know the final temperature, so I'm just going to call that X minus the initial temperature of the water. It's in a cold room at room temperature, 19 degrees Celsius, equals. Now, M for the brass. We're given the length of each side of a cube and the density. So, if I start with the density of the cube, 8.25 grams per centimeter cubed, and multiply that by, let's see, 22 milliliters is 22 millimeters is 2.2 centimeters. And I need to cube that. When you do, you get 10.6. Multiply that by 8.25. And I got 87.8 grams. Alright, and it's negative. I forgot a negative sign here. So minus 87.8 grams times C, 0.362 joules per gram degree Celsius. I'm going to leave units here because I'm running out of room. And then temperature, final, I don't know, minus initial, 85 degrees C. All right, so let's just talk through conceptually what's happening here. We would expect that the temperature of the water to rise from 19 degrees Celsius when you add the 85 degrees Celsius brass to it. So the final temperature we can predict will be somewhere between 19 degrees and 85 degrees. So if I have, let's just guess for a minute that it's 50. If I put a 50 here for this X, I get a positive number. But that same 50 here, I get a negative, right? And that's what this negative accounts for, okay, is that the temperature will drop for the brass. Now from this point, it's just some algebra. So the first thing I did was multiplied 20 times 4.184, okay, and I got 83.86, and then I just distributed that to each part of these parentheses. So first I have X, and then when I multiplied it by 19, I got when I multiplied by negative 19, minus 1589.92 equals, I did the same thing here. I multiplied negative 87.8 and 0.362. And when I did that, I got negative 31.9 0.78, and I need to distribute that to both terms here. So that would be x and plus 2701. Well, I guess so 2702, approximately. All right, so we just have a linear equation here, and we just need to get x by itself. So everything that has an x goes on one side of the equal sign. Everything that doesn't have an x goes on the other side. So I get 115.46x equals 4291.52. And I get x, which remember that's my final temperature, equal to 37.17 degrees.